So what's the meaning of half equivalence point? What it shows that when half of the acid is reacted, so when half of the acid is reacted, that time the concentration of the acid will be same as concentration of the salt which is formed due to reaction of acid. So when we write the dissociation constant, because actually when we write Ka, dissociation constant of acid is the product is a ion which is formed by the acid. So they have the same concentration. So we can cancel out these two, and we can say hydrogen ion concentration is equals to Ka. Or if we take negative log of hydrogen and negative log of Ka, so we can say pH is equals to pK. So example, what is the pH of a resultant solution when 25 cm cube of 0.1 mole sodium hydroxide is added to 50 cm cube of 0.1 mole ethanoic acid? Dissociation constant is 1.7. So if the concentrations are same, you can see the concentrations are same, so the volume of sodium hydroxide is half as compared to volume of ethanoic acid, and the simplest ratio for this reaction between them is 1:1. If you have ethanoic acid, so 1 mole of ethanoic acid is reacting with 1 mole of sodium hydroxide. This will result in a formation of sodium ethanoate plus water. So 25 cm cube 0.1 and 50 cm cube 0.1. So concentrations are same. So the volume and the simplest ratio between them is 1:1. But how much volume of sodium hydroxide? 25 cm cube, and volume of ethanoic acid is 50. So volume of ethanoic acid is twice. It means half of the ethanoic acid will react and remaining half will be there unreacted. And how much salt will form? The same equal amount of concentration of salt will form. So the concentration of acid and the concentration of a salt will be same. So they can cancel out with each other, and we can say pH is equals to pKa. So Ka was given, we can take minus log of Ka to get the pKa. And what is the value of pKa? That is same as the pH. So without doing much calculation, we can work out the pH of the solution. Is it clear? The concept of half equivalence point, which is used to work out the pH of weak acids. Any doubt till now? And if we are diluting an acid, diluting means like adding water, it's a dilution. So if we are diluting acid and alkali, so the hydrogen ion concentration will change. How to find? So the new hydrogen ion concentration is equals to old hydrogen ion concentration multiplied by old volume divided by new volume. And same thing, if you need a hydroxide concentration, new hydroxide concentration, if because we are diluting a solution, so diluting a solution means adding water, so the volume of a solution will change, or solution sometime when a reaction occur, the solution also diluted because acid and alkali both contain water. So the formula is for a new hydrogen ion concentration is old hydrogen ion concentration multiplied by old volume divided by new volume, because actually the moles will be same. It's not a new formula. Actually in both solution, when you are diluted or concentrated solution, both will have equal moles. So moles in because we are not adding a reactant, so moles in dilute solution and moles in concentrated solution will be same. Moles is concentration multiplied by volume. So you can say concentration multiplied by volume is equals to concentration multiplied by volume. So if I say this is a new concentration, new volume, old concentration, old volume. So if I need new concentration, I will just divide the product of concentration and volume by new volume. So in this question, calculate the new pH when 50 cm cube of 0.150 mole per HCl is mixed with 500 cm cube water. So what happened? Basically, adding a water make a solution dilute, and we need a, so they will have the same moles, so concentration into volume. So we can use the formula C1V1 equals C2V2, or I can use this formula. That's the same hydrogen ion concentration. What is a hydrogen ion? It's a strong acid. For strong acid, the hydrogen ion concentration is same as the concentration of acid, so that's why it's 0.150. The old volume was 50 cm cube, which is 0.05, and the new volume. What is the new volume? Because you can see originally it was 50 and we added 500 more. So it will not be like 500, it will be 550. That's why it is 0.55. When you solve, you'll get the new hydrogen ion concentration. Using a new hydrogen ion concentration, you will get the pH. Is it clear, this example? How we work out the concentration of new solution which is diluted by adding 500 cm cube of water. So when we compare the pH of a strong acid and weak acid after dilution 10 times or 100 times or 1000 times, so for strong acids and for strong acid and strong alkali, if it is diluted 10 times, 100 times or 1000 times, so the pH will have a greater change, because as we know, the pH is in a logarithm scale, like pH is equals to minus log of hydrogen ion concentration. So if we dilute the strong acid 10 times, and what will happen if diluting, so concentration of hydrogen, because diluting means concentration is moles over volume. Moles we are not changing. Diluting a solution, we are increasing a volume, so we reduce the concentration. As the concentration of hydrogen ion decrease, the pH will increase. So if we dilute 10 times, the pH will only change by 1 unit. Like example, if in, so original pH was 2, and solution is say 5 cm cube, solution was there, and we are diluting 10 times, like we make the solution 50 cm cube, total volume, adding 45, so that total volume is 50 cm cube. So if the dilution factor is 10 times, then what happened to the pH? pH will increase by 1 unit, so pH will turn into 3. But if a dilution factor is 100 times, then what happened? The pH will increase by 2 units, so pH will become 4. If dilution factor is 1000 times, then what happened to the pH? The pH will increase by 3, so it will become 5. So every time, like if dilution factor is multiplied by 10, change the pH of a solution by 1. This is only valid for strong acid, but it is not valid for weak acid. Why for weak acid it's not equal to 1, it is less than 1? Because weak acids already, they have very small amount of hydrogen ion concentration. So dilution does not make too much difference or very small difference to hydrogen ion concentration. That's why the pH will not change with the same rate as for strong acids. Is it clear? So you can see here, for a weak acid, say propanoic acid dissolved in water gives hydroxonium ion and propanoate ion. Now what we are doing, diluting means we are adding water. So dilute the weak acid pushes the equilibrium towards right. Why? Because we are adding water. So if I add water, I add reactant, equilibrium shifted towards right. So if equilibrium shifted towards right, so degree of dissociation increased. So hydrogen ion concentration also increases and produce, like hydrogen ions are produced, which means pH increase in a less expected rate. But in the other one, because when HCl was there, strong acid, already it is ionized. So when I add water, it will not make any difference to the hydrogen ion moles. It only change the volume of the solution. But in this case, the volume of a solution is also affected, and the moles present at equilibrium for hydrogen ions are also affected. That's why it will not give the change with the same factor as it is for strong acids. Is it clear? Then what is a buffer solution? A solution which resists the change in the pH. If a small quantity, that's important thing, is not like you add too much. If you add a small quantity of acid or alkali and the solution does not change the pH, we call that solution as a buffer solution. You can have an acidic buffer solution or you can have a basic buffer solution. Acidic buffer solution is a mixture of weak acid and its salt, and basic buffer solution is a combination of weak base and its salt. How the buffer solution works, that's the important thing. So, and how buffer solution can be formed. For example, if you are reacting a weak acid, if there is a weak acid is reacting with a strong alkali, this will result in a formation of a salt of a weak acid and water. Example, weak acid is in excess, excess means more than enough, and alkali is a limiting reagent. So if alkali is a limiting reagent, alkali will be used up. So what you're left with, weak acid and its salt. So a solution which contain weak acid and its salt, that solution is known as a buffer solution. Or you can also form a buffer solution if we have weak base and strong acid, and that acid is a limiting reagent. So acid will be used up, it will form a salt plus water. So you can see you're left with weak base and the salt of the weak base. That's why it is also known as the buffer solution. So buffer solution is a combination of weak acid and its salt and weak base and its salt. How it how it resists the change in pH, that's the second factor, like second point. So how a buffer solution work? For example, if we are taking example of say a buffer solution, acidic buffer solution, because a buffer solution can be acidic, a buffer solution can be alkaline. So if you have an acidic buffer solution means a solution which is a combination or a mixture of weak acid and its salt. So weak acid is there and the conjugate base or its salt is there. So weak acid will dissociate into the, like example, you have ethanoic acid, it will dissociate into ethanoate ion and hydrogen ion. And if we add a small quantity of acid, like example, if we add small quantity of acid, then what happen? This is there like the dissociation, and already what we have a reservoir, because this solution is having, it's a weak acid and it's salt. So this salt will be CH3CO ion and Na plus ion, and weak acid is dissociating into CH3CO, but a small dissociation into H plus. For example, if we add an acid to this mixture, so if I add an acid, what happened? You can see the equilibrium will shift toward left hand side. Why equilibrium will shift toward left hand side? If you add an acid, amount of hydrogen in the solution increases. So if I add one mole of acid, it will form one molecule. So as the equilibrium is shifted towards left hand side, so as the equilibrium is shifted toward left hand side, so addition of the quantity of acid does not make difference to the hydrogen ion. Like originally, if I was having 10 hydrogen ion, I add one more. So if I add one more, the moment, because it is already in equilibrium, the moment when I add one more, that one more hydrogen ion will react with acetate ion and form ethanoic acid, because we have a reservoir, we have excess of acetate ion. So hydrogen ion can react and form the molecule. So addition of that hydrogen ion or acid does not make difference to the hydrogen ion concentration. So pH does not change for a small, significantly small amount. If you add too much, definitely there will be a change in pH, but for a small amount, there is no change in pH. Same thing if we add an alkali, if I add an alkali, like I will add OH. So if I add an alkali, that OH ion react with hydrogen ion, so amount of hydrogen ion will decrease. So the molecule will dissociate and form the same number of hydrogen ion, because already we have these ethanoic acid molecule which are greater in number as compared to that of ethanoate ion or hydrogen ion. So if we add a small amount or quantity of the alkali to the buffer, so the hydrogen ion and hydroxide ion will react, form water, and what will happen, it will shift the equilibrium towards right, and it will produce same number of hydrogen ion. Like if I add one hydroxide ion, one hydrogen ion is removed from the solution. To overcome this, a molecule will dissociate into ion and release the same. So it will not make any difference to the solution, the hydrogen ion concentration. It does not make any difference to the hydrogen ion concentration. That's why it resists the change in pH. So weak acid and its salts, or weak alkali and its salt, can act like a buffer, or does not. If we add a small quantity of acid and alkali, it will not change its pH. Is it clear, the buffer solution? So it resists the change in pH or try to stop the change in the pH. Is it clear how the buffer solution works? So what is the advantage of having this? You can see when we write the dissociation Ka, dissociation constant for this weak acid. So the Ka dissociation constant is equals to product, which is CH3COO, hydrogen ion, and CH3COOH. Or if we want hydrogen ion concentration, so hydrogen ion concentration, when we just rearrange the equation, the hydrogen ion concentration depends on Ka. K is constant, and also it depends on this ratio. The ratio of the molecule, the concentration of acid divided by its salt. So if this ratio does not change, it means the hydrogen ion concentration will not change. If hydrogen ion concentration will not change, it means the pH of the solution will be constant. So as you can see, the first one, we have a reservoir, like too much salt is there in this. So if a small amount of acid is added, the above equilibrium shifted toward left hand side. So if it is shifted toward left hand side, what it result? It will produce and nearly all hydrogen ions which are added are balanced, and it will produce this acid. As a large concentration of a salt is there, so this concentration is too large, so a small change in this value will not make much difference to the hydrogen ion concentration, so pH will remain unchanged or pH will remain constant. And same way, if we add an alkali, equilibrium shifted towards right hand side, so we get more CH3CO, but already it is in a large amount, so small increase will not make much difference. So the hydrogen ion concentration will not change. Result, there is no change in pH. So how we can calculate the pH of a buffer solution? So simply, it's a same formula as we know. If we have a weak acid, example, this is a weak acid, it will dissociate into hydrogen ion, and a negative ion is there, Ni. So when I write Ka for this acid, this is a product divided by reactant. So hydrogen ion, the negative ion which is formed due to this acid dissociation, and Ha. So if I need hydrogen ion, so Ka will be multiplied to, so Ka, this is concentration of acid divided by concentration of salt is equals to hydrogen ion. So if I know the concentration of acid, I know what is the concentration of a salt, and Ka, I can work out hydrogen ion, and using hydrogen ion, I can work out the pH of the solution. So example, making a buffered solution by adding a salt, what would be the pH of a buffered solution? Because buffer solution, you can make buffer solution by mixing a salt with weak acid, or you can carry out a reaction between weak acid and limited amount of alkali. The concentration of alkali, the moles of alkali will be same as moles of salt which is formed. So using that, you can also work out the pH. So there are different ways to prepare the buffer solution. One of the ways is mixing salt solution, aqueous acid, weak acid with salt solution. A second way, reacting acid with a limited amount of alkali, weak acid with limited amount of alkali, that also result in a formation of a buffer. So what would be the pH of a buffer solution made by 45 cm cube of 0.1 mole ethanoic acid and 50 cm cube of 0.1 mole sodium ethanoate? Now, so the formula, as we know, the hydrogen ion concentration is Ka. What is this? This is a concentration of acid, and this is a concentration of salt. So what is the concentration? First, because what happened, we are mixing ethanoic acid with a salt or sodium ethanoate. So originally the concentration is given, because what will happen, the you can substitute the moles, otherwise this concentration will change. Why this concentration? As you can see, originally we were having 45 cm cube of 0.1 mole ethanoic acid, and we mix with 50 cm cube of 0.1 mole, 0.15 moles of sodium ethanoate. That's the original. But when we mix them together, their concentration will change. How the concentration will change? Because this is the original volume, original concentration, new volume will be 45 plus 50, which is equals to 90. So it will increase like the steps in the calculation. So to overcome this, what you can do, you can substitute the moles here. Why you can substitute the moles? As you can see, hydrogen ion is equals to Ka, dissociation of acid, the concentration of acid, divided by concentration of the salt. So instead of substituting concentration, I can substitute moles here. Why? Because moles divided by volume and moles divided by volume. So volume will cancel with volume. So I will have their moles. So I can substitute the moles. Otherwise, what you have to do, as you want to use a formula to find the hydrogen ion concentration, so you need a new concentration. So how you can get the new concentration? So you have the formula C1V1 equal to C2V2. If I want to find a new concentration of acid, original concentration is 0.1, original volume is 45, new concentration I don't know, and the new volume, because we mix as salt solution with acid 40 and 50, so that is equals to 95. I'll get the concentration of acid. Same way, I will use the same formula to get the new concentration of a salt. C1V1 equal to C2V2. So C1 is the original concentration of the salt 0.15, original volume 50, new concentration we don't know, and the new volume is 90. I'll get the concentration of salt. So I have their concentration, K is given, I can find hydrogen ion, and using hydrogen ion, I can find the pH. This is one way. The second method, I will find the moles and substitute the moles here because the volume is same for both. So volume is same, volume moles divided by volume and mole divided by volume. So volume of volume cancel. So I can take a ratio of the moles, and using that mole ratio multiplied by Ka, I can find the dissociation constant. I can find the hydrogen ion, and using hydrogen ion, I can find the pH. Is it clear how this question can be done two ways? Any doubt in this part? Another example, making a buffer by adding a solid salt. So if you're adding a solid salt, so the volume of the solution will be same as the volume, original volume. Only the moles of the concentration you will work out. So as you can see in this question, a buffer solution is made by adding 1.1 gram of sodium ethanoate to 100 cm cube of zero point 0.4 mole ethanoic acid. What is the pH? K is given. So first I can work out the concentration. Moles equal mass in gram over molar mass. So mass in gram is 1.1. I'll divide by a molar mass, which is 82. I'll get the moles. And after getting a moles divided by volume, I'll get the concentration of ethanoic acid and concentration of, in this case, the acid concentration will remain same. Why the acid concentration is not changing? Because the total volume of the solution is 100 cm cube. So the total volume of a solution does not change. So acid concentration does not change. So instead of substituting the mole, the best is always substitute the concentration. Here, the concentration of acid will remain unchanged, but concentration of salt we work out by using a formula moles divided by volume. Moles mass in gram over molar mass, which is 0.0134, divided by volume was 100 cm cube. So it will be divided by 0.1. We'll get the concentration, and K is there. We can find pH. So you can, so in the first example, we were having two solutions having a different amount of acid and alkali, sorry, different amount of salt solution is there and acid is there, and we mix them together. That was the first question. But in this question, we have a aqueous acid, so dissolved acid, and we are adding a salt to this. So when we add a salt to this will dissolve and it will make a buffer solution, but the total volume is unchanged. Here, The total volume was the sum of the two solutions. Is it clear, this part? And the third method of making a buffer solution is by reaction of partially neutralization, means a limited amount of alkali is added to an acid. Acid is an acid. So example, you have 55 cm cube of 0.5 mole, and these type of questions are common. Reacted with 25 cm cube of 0.35 sodium hydroxide. What will the pH of the resulting buffer? As we know, sodium hydroxide is a, when we work out the moles, so when we work out the moles of ethanoic acid and sodium hydroxide, the ratio between them is 1:1. So you can see sodium hydroxide moles are limited. So it's a limiting reagent. So sodium hydroxide is a limiting reagent. It will be used up completely. So what you're left with ethanoic acid and you're left with sodium ethanoate. But to get a pH, first we'll find hydrogen ion. We know hydrogen ion is equals to Ka for a buffer solution, concentration of acid divided by concentration of the salt. But now, because the original moles are not same as the moles left in the solution, so original moles were 0.02, but how many moles are left? Because the ratio is 1:1, if 0.00875 moles of sodium hydroxide, X moles will react, and how many are left? So you will subtract. When you subtract, these are the moles which are left for ethanoic acid. So if these are the moles which are left for ethanoic acid, you can find the new concentration. You have the moles and divided by volume. What is the volume? Because you mix 55 cm cube of acid with 25 cm cube of alkali, so total volume is equals to 80 cm cube, which is 0.08. So this is a new concentration of ethanoic acid, because unreacted moles of ethanoic acid are there, and that will change the concentration of ethanoic acid in the solution. And what about concentration of the salt? As we know, the ratio of sodium hydroxide and sodium ethanoate is 1:1. So same number of moles of sodium ethanoate will be formed, and divided by the volume, we'll get the concentration of sodium ethanoate. So we'll use the formula. We have the concentration of acid, we have concentration of the salt. K is given in the question, so we can find hydrogen ion, and using hydrogen ion, we can work out the pH of this buffer solution. Is it clear? This is the third type of a question in which you're finding a solution. This is how we worked out. Any doubt in this part? So next class we will discuss acid base equilibria, questions from the past paper, and the last topic of this one, titration curve. So next week I will explain, and we'll discuss questions from this topic, acid base equilibria. Any doubt related to the class today?